record. So good afternoon, folk. Thank you so much for joining us for our webinar. My name is Simon Corbey. I'm the Executive Director at the Alliance for Sustainable Building Products. And we're gathered here today to look at our work funded by the Fire Services Research Training Trust. So we're going to talk you through that. I'm going to wait for just a couple more minutes for people to join us. So make sure you've got a glass of water or two to hand, and hopefully it's not too hot. It's pleasantly warm where I am, but it's not too hot, which I am grateful for. So I'm just going to wait a couple more minutes for everyone to come in, and then I'll make a start. So we're just here for an hour today. We'll make sure we finish promptly at 2 o'clock. Yeah, so I'm going to make a start now so that we keep to time. So the program for today is you've got 5 minutes of me just introducing the Alliance for Sustainable Building Products and having a few words from the Fire Services Research Training Trust, who are the funder for this project. And then I'm going to hand over to Ashley, so from the National Fire Chiefs Council. So NFCC was asked to provide a letter of support to the project, which they kindly did. And Ashley is here just to tell us a little bit more about what the National Fire Chiefs Council do and how they work. So thanks ever so much, Ashley, for joining us today. And then at 1:10 I'm going to hand over to Dale. So Dale is from the Fire Protection Association. So the RISC Authority were a project supporter, and the tests that we did were conducted at the Fire Protection Association laboratories. And then from Dale, we'll hand over to Professor Jim Glockling, who's going to talk us through the test procedures and then the solutions. And then we're joined by Nigel Rogers from Midfix. So Nigel was kind enough to supply all the fixings that we needed to do all the tests. And we're going to ask him just for a few initial thoughts and reflections on the projects and the results. And then we've got a bit of time for some questions and answers, and then we'll wrap up at 2 o'clock. So just a little bit of housekeeping. If you've got questions to ask, and hopefully you will, pop them into the Q&A. You can see we've got a Q&A function at the bottom on the toolbar. So pop them in there. And if you see a question that looks a bit similar to the one that you had in mind, just upvote the one that's there. And I'll deal with questions that have been upvoted the most as we move on to Q&A at the end. So just a reminder that we are recording the session. It will be freely available to anybody and everybody. It'll be hosted up on our YouTube channel, and we will share the slides with everybody on this webinar. But feel free to forward those on, and we'll let you know when the recording is available. It takes us a couple of days to edit it. So please keep your microphone muted for the moment. Any technical issues, just pop something in the chat. So my colleague Richard is there to help out. And then if you want to, you can ask a question anonymously rather than put your name to it. So just a quick slide about the Alliance for Sustainable Building Products. We're a not-for-profit sustainability organisation. We're all about healthy and low carbon. So we aim to sort of move this agenda forward through events like this. We conduct some research projects, and I'll talk about those in a second. We aim to develop best practice guidance, and we aim to collaborate and work across the entire industry. We are an advocacy organisation. We are aiming to try and convince government that they need to do things and look at, say, for example, embodied carbon and whole life carbon. So that's an ongoing process for us. We have a focus that looks at natural materials, but We have work streams on health and well-being. We have a reuse now campaign. We have a work stream that focuses on mass timber, embodied carbon, and many more. Just visit our website. There's a QR code there. Sign up to our free newsletter. And we are a membership organisation. We're growing all the time, but we would welcome your interest. The more members that we have, the bigger the voice we carry. So just a few current related research projects we've got on the go. So the first one is the one we're looking at today. After that, we've been looking at sprinklers and how they may act as an enabler for low carbon buildings. We're aiming to launch that in September. After that, we're looking at water and moisture in mass timber buildings and how we can manage that through the life course. Jim is leading that work, funded by Swedish Wood and the American Softwood Lumber Board, and aims to wrap up towards the end of October, later on in the autumn. And then lastly, we're working on a project around damage assessment and remediation pathways for timber buildings, and that's kindly funded by Built by Nature, and that wraps up next year. So some exciting research projects underway. So as I said, do sign up to our newsletter so we can keep you up to date with events, and if you want to get involved in the projects, just let us know. All right, so I wanted to say a big thank you from the Fire Services Research Training Trust. They're a new funder for us. So Alistair Hay asked us to say a few words on his behalf. So they were pleased to support the project and felt that it was professionally managed and conducted. And they're keen to encourage more applications. They've asked us to, if we've got any subjects that we want to look at, to move on to the next project. So happy to take any ideas or work up a team. But if you're interested in finding out a bit more about the Fire Services Research Training Trust, their website is there. So huge thank you to them. And then a big thank you also to the RISC Authority and the Fire Protection Association, as I suggested. They supported the project, and we carried out the testing at their labs. KLH, Nick Clark, was kind enough to supply a whole chunk of CLT free of charge for us to enable us to do the testing. We're eternally grateful to Nick. And Nigel is on the webinar today from Midfix, and as I said, they were kind enough to supply all the fixings that we needed. And Nigel's been incredibly helpful through the project as we've tried to learn from him through his skills. All right, well, that's enough of me. So I'm going to hand over to Ashley Mather. So he's the Senior Fire Engineer at the National Fire Chiefs Council. So Ashley, I'm going to ask you to take yourself off mute and step forward to the virtual podium. And yeah, thank you very much. And we look forward to finding out a bit more about the National Fire Chiefs Council.
Thanks, Simon. And I was wondering where you got that photo from, and then I realised I willingly sent it to you. So that's on me. But yeah, thank you. Hello, everybody. As Simon said, my name's Ashley. I'm a fire engineer with the National Fire Chiefs Council, NFCC. So for those of you that may be less familiar with NFCC, we are a membership organisation whereby fire and rescue services making up the vast majority of our members. And our role is to support them across everything they do in their three core areas of work: response, protection, and prevention. So that means developing national operational guidance to support firefighters responding to emergencies, producing guidance, policy, and providing technical advice on the regulatory side of fire safety, and supporting prevention initiatives that help reduce the number of incidents through education and risk reduction. And alongside this, NFCC works closely with government, regulators, industry, and other professional bodies to influence the development of legislation, standards, and fire safety guidance. We want to ensure that the practical experience of the Fire and Rescue Service helps inform national policy and future regulation. And in undertaking those activities, one thing that we constantly push for is that whatever policy decisions are made, whatever guidance is produced, that they are informed by robust evidence. because fire safety is a discipline that continues to evolve. Construction methods and materials are constantly changing and bringing new opportunities, but also new challenges. And as NFCC, it's fair to say that we do have concerns regarding modern methods of construction in its various forms, including mass timber, which is the focus of today's research. However, I think it's important to recognise that our concerns stem more from the drive to adopt these methods despite a lack of evidence of real world performance. What does constructing buildings in this way mean for both public and firefighter safety? To keep pace with that change, we need to continually improve our understanding of how buildings behave in fire. And this means moving beyond assumptions of tradition and basing our decisions on sound research and evidence. Whilst there's a significant amount of fire research undertaken across academia and industry, I'd suggest research specifically intended to support fire and rescue services, inform operational policy practices is comparatively uncommon. We know that the government, as part of their ongoing technical review of ADB, has commissioned research into access and facilities for firefighting to help inform future guidance, although I don't know what that involves. Regardless, where opportunities arise to strengthen that evidence base, NFCC are keen to support. And that is one of the reasons that we, as an organisation, established our Academic Collaboration, Evaluation and Research Group, also known as ACER. So ACER brings together representatives from fire and rescue services, academia and industry with a shared ambition of strengthening the relationship between research and practice. The group has identified research priorities, it encourages collaboration, promotes high quality evidence, and supports the translation of research into practical improvements in guidance, standards, and operational policy. The NFCC, through the ACER group, was pleased to support the funding bid to the Fire Service Research and Training Trust for the research that you're going to hear about today. We recognise that this is an area where strengthening the evidence base had the potential to assist not only designers and engineers, but also fire and rescue services and obviously ultimately the safety of the communities that we serve. Research has the greatest impact when it doesn't remain within academic papers, but is shared, challenged, and discussed by practitioners. It's through conversations like today that evidence begins to influence guidance and standards, and ultimately the way that buildings are designed and constructed. So with that, I'm going to stop speaking now, as I'm very conscious to not steal the thunder from Jim and Dale, who have undertaken this work and are far better placed to explain both the research and its implications. Thank you very much.
Lovely. Thanks, Ashley. For those of you who couldn't see, so Ashley didn't have any slides, so you needed to put your view on speaker. So I'm going to hand over to Dale. So Dale's now started to screen share, so that looks great. Thank you, Dale. So over to you. You're on mute, Dale.
Is that working now?
Brilliant.
That's great. Good afternoon and welcome. I'm just going to discuss this afternoon and try and cram in as many slides as I can in the 10 minutes that I have to discuss some research that I've been conducting for the last 4 years on fire protection systems of mass timber buildings. As you can see on the screen there, we've done this in partnership with ASBP, NFCC, RISC Authority, which is the company that I work for, Glockling Consulting and Midfix. It's already been discussed how we do it. But this particular piece of research that I'm going to discuss today is actually part of a research that I've recently done for a degree, award of PhD. So just running through what we actually got, what is the difference between and what is the problem? Obviously, we're replacing traditional construction materials that have known fire performance with combustible materials. So as you can see on the screen there, we're transitioning away from standard steel and concrete, and we're moving into the CLT, the glulam beams, etc. type of alveol timber business. And the problem with it is combustible, irrespective of what some scientists say. What are the dangers and what have we learned from the past? Well, recently this just gives you an idea of the problem that we've got in an unsprinklered building. So my study was basically to look at sprinkler systems with regards to how we can best manage the use of construction materials such as timber in the built environment. To know where we've gone from and to know where we're going is, have we learned the lessons from the past? So if we go back to 1666 and the Great Fire of London, that was under the King Charles II. And we decided that we were not going to be building out of timber. We were going to be building out of brick and stone and widen the distances between buildings and widen roads. Now, under King Charles III, the current government, under their aspirations for net zero, are looking at building into timber, which is fine, but it does bring with it a problem. So have we learnt the dangers from the past? Well, we know it's combustible. So through the University of Lancashire, I commenced a degree in 2022 and looked at adapting sprinkler systems to better protect the combustible surfaces. So that was what I suppose my hypothesis was: how can we adapt a sprinkler system to better protect the exposed timber, also the hidden timber, which causes a bit of a problem because timber has the ability to smoulder. So we want to stop fires going into the voids. We also have a water sensitivity with regards to timber because it can rot. We get dry rot and wet rot, and we get infestations. There's another issue with regards to there. And that was basically the aim of my project. However, it transitioned from a one objective to two objectives, where we looked at, well, I found that the issue is, how do I actually fix sprinkler pipework to the underside of CLT? So there was an issue that came up. So the PhD, it transitioned from a master's degree to a PhD, and the study focused on two separate areas. So area one, which I'm just going to go through a few quick slides, is that we looked at the spray discharge of sprinkler systems so that we could provide some form of better protection to the exposed combustible surfaces. And the second part of the study was, how do we fix not just sprinkler pipework, but M&E services to the underside of timber soffits. This was also highlighted in the white paper that the RISC Authority, which is a majority of UK insurance, they looked at the insurability of mass timber buildings, and this paper was produced some probably 3 or 4 or 5 years ago through RISC Authority, and it highlighted the problems. It also looked actually in detail at automatic suppression systems, and the first thing that they've actually pulled out there is the fact that whilst we have standards for various other types of suppression form, it's only sprinkler systems that have a focus on property protections where the insurer is interested in, the LPC rules. So again, that fed into the requirement for me to do the research and how better to protect these buildings. So the first part of the study, I looked at sprinkler heads. The idea was that we looked at the marketplace, what current sprinkler heads are still available, and what the requirements were for the spacing of sprinklers. And the goal, as you can see on the screen there, was to assess whether we've got standard sprinklers can better protect exposed timber surfaces. So the 3 types of sprinklers that are still currently available in the marketplace are pendant sprinklers that spray water downwards, upright sprinklers that spray water downwards, and a conventional type of sprinklers that can spray a little bit of water upwards and a little bit of water downwards. So we investigated this further. The idea of the investigation was to make sure that we could provide surface wetting from the sprinkler system. So by the use of a specific type of sprinkler, we could confirm that an upward spray from the sprinkler could provide a surface wetting, as you can see on the top left-hand corner of the screen. The second most important value was the fact that it is always assumed that the fire will start in the movable fuel load on the floor. So there is a requirement under the standards that you must achieve a certain density of water based on an occupancy risk. So floor coverage was the second most important factor that we looked at. And the third, can we use the sprinklers to provide wetting of the walls to stop surface spread of flames up the wall? And this work was all done, tested in the laboratory at the FPA. And I'm not going to go on to it because there's a scientific paper at the end of my conclusions that just shows you all about the work that was done if you wanted to be interested in the sprinkler side of things rather than the fixings. But in short, the conclusions show that there is one type of sprinkler that met the requirements for providing water upwards. It's a conventional type sprinkler. It provided water upwards. As you can see on the bottom right-hand picture there, it provided the required density to meet the movable fuel load on the floor based on the occupancy risk classification. And on the left-hand side there, you can see that the sprinkler itself provided water spray across the ceiling and down the walls. Therefore, we are trying to cover every eventuality of a fire within a compartment to provide wetting of the surfaces to slow the spread down. This was done for the PhD, not part of this actual Fire Service Research Training Trust. And following this work, as you can see on the screen there, there's some new documentation which Simon's already mentioned. It's going to be launched at the end of September. We have reviewed it with the RISC Authority and the Sprinkler Rules Working Group, and obviously the document highlights the myriad of benefits that we can use sprinkler systems to address insurance challenges that are been presented by mass timber. So that's enough of that particular study. The second part of the study, which I think you'll be more interested in, is obviously fixing investigation. So we know it behaves completely different. We've also had past incidents. So we had the Shirley Towers. We had services falling from Shirley Towers, which led to the deaths of 3 firemen. We understand that the industry, when we started this research, there was no European standard, there was no national standard, there was only a little bit of guidance, but nothing was ever tested in timber. So we undertook the testing of timber. We designed our own bespoke test rig, as you can see there, and Jim will go on to elaborate about this a little bit later, because we took this to the next level with the training, with the testing with the Fire Service Research Training Trust. But we designed a bespoke rig which allowed us to put a 0.81 cubic meter ceiling of timber and a rear wall of timber using an ISO 9705 burner, and inside, underneath the ceiling, that was fixings. They were mounted into the ceiling, and with lots of measurements. So we designed it to simulate ceiling mounted service installations and a corridor type file on medium scale risk. The test samples were a 900 by 900 by 180 mil thick, and it was a 5-ply, which is typical of a floor and a ceiling configuration of CLT. There was 2 types of glues. There was a standard PU glue and there was a modified fire rated PU glue. All the panels were put into a conditioning chamber before, so that they were all the testing could be tested at the same level of moisture content. And the fixings, as provided by Midfix, we looked at what kind of fixings do we need. So we tested fixings that met the minimum requirements of the sprinkler standard, which is BSEN 12845 table 10. And that table pretty much eliminates anything lower than M10. So we looked at M10 and M12 coach screws into timber. We also tested some M8, and on behalf of the sponsors, we tested some stud bolts and rod hangers, A to F, as shown on the picture. We also tested them at various embedment depths. So we started at 50 mil embedment depth, going up to 110 mil embedment depths. We were limited by the stud hangers and rod hangers to a depth of 60 mil. And this test data is available in the paper, excuse me. We took numerous measurements throughout the depth of the timber. So we took locations of every full ply. We took measurements of the glue line. We took measurements of each fixing. So we did the exposed side to the fire, the midpoint of a fixing, and the top of a fixing, so that we could measure the heat of conduction through the screw. We did tests at 30 minutes and 60 minutes. We also did 5 ambient tests with all these fixings, just to measure the pull out results. So we could use that as the benchmark as to what the capacity of the fixings were in a non-fire situation, so at ambient conditions, what the load capacities were. And then we did the tests at 30 minutes and 60 minutes. On completion of the tests, we carefully scraped away the char that had built up underneath the panel to expose the fixings, as you can see on the bottom there, and bottom right, sorry. And just above that, that was the pull-out testing device, the digital tester that we used to find out all the results from the tests that we did. So we did 13 fire tests in total, and that pulled all together into one nice graph. The results show there. So looking at the graph, what's highlighted there is we've got the pull-out force up the left-hand side and the embedment depth on the right-hand side. And as you can see, the load diminishes with embedment depth. So the shallower that you've got the fixing, the less load you can carry with that particular fixing. The 2 dashed lines in at the top are the ambient temperatures, and what you can see significantly from there is that the M12 fixings held stronger than the M10 fixings. However, when you introduce the fire, it flips around the other way. So there is an issue with regards to diameter of fixing versus fire. And what we found is that the larger diameter fixings carried less load than the thinner or the skinnier or thinner diameter fixings. And the four lines on the left hand side of the graph just represent 30 minutes. It's the dotted line, and the dashed dot line is the 60 minutes. So as you can see, as the fire duration goes, you're losing load. And just along there, we looked at the British standard requirement for sprinkler systems, which is a 500 kilogram load, which we've just replicated on there to see where the fixings lay with regards to ambient temperatures. So the results, as we can see in there, that larger diameter fixings are stronger at ambient, but they aren't under fire conditions. Post-fire pull-out strength is greatly reduced based on the fact that you've lost some of the char. And we also conducted 4 of the tests with loads on there. We had a 150 kilogram load on some of the fixings that they were failing during the fire, circa 20 minutes. So the conclusions on the study that I've done is basically that the fixings that we tested at M10, M8, M10 and M12 met the load requirements at ambient temperatures. We know there's not an issue there in a non-fire condition, but under fire conditions, we're losing surface material. We're losing that to char, which contains no structural capacity in it at all. We also found that we had conduction of heat through the fixings into the timber. And as you can see on the top right there, we were getting localized charring around the threads, and the interface where the threads met the timber, it weakens the timber, causing charring. At the bottom, you can see the char below the panel. We were losing that. So your embedment, to say it started at 110 mil, may only be 80 mil after a 30-minute fire, or 70 mil after a 60-minute fire. So you're losing that capacity for the fixing to hold into there during a fire. We found that the larger diameter fixings conducted more heat, and we were getting greater losses in the larger fixings. So we found the problem here. We hadn't actually found the solution. The paper, or the scientific data that's behind it, is available in these scientific papers here. So both papers, we have a sprinkler paper on the left-hand side there. Both papers have been published through Fire Technology, and the links are available. So on the left-hand side, all the data, all the graphs and the methodology with regards to the sprinklers is in the paper on the right, on the left-hand side, and on the right-hand side is the paper related to the work that we've been doing. And Jim will take over this presentation now to tell you all about the Fire Service Research Training Trust. So hopefully that's given you a flavour of the findings and the problems that we found during my research. And once we'd found that and we published this paper, the paper that's shown on the right-hand side, was then the fact that the alarm bell came on, a light bulb moment, we need to do something about it. And then I will now hand over to Jim to tell you where we took it from here. Thank you.
Thanks, Dale.
Good.
If
Thank
I could
you very
ask you
much,
to
Dale.
stop sharing, Dale. Brilliant. So
Right, hopefully you can see my screen now.
we can. Thank you, Jim.
Right, well, first of all, I should congratulate Dale on an absolutely outstanding PhD. And it's one of those delightful occasions when you go looking for one thing and then you find another very, very important thing, and afforded us the ability to go well armed with data to the Fire Service Research Training Trust, who were very receptive, saw immediately the challenge presented, and put up significant funding for us to do this piece of work here, where we were looking for solutions and really looking for an overall sort of overarching sort of theory of why everything was happening this way. So I'm going to go quite quickly through this, but I understand that these slides will be made available, and also the webinar also. So the thing the thing that was recognised following Dale's research is that there are implications on a timescale for life safety in terms of the well-being of evacuees and the attending fire services. And anyone who's seen me talk about mass timber before, because of the nature of the way mass timber performs in fire, I do honestly believe that the fire service are going to be absolutely crucial in the resolution of any fire within them. It requires boots on the ground, predominantly because of the ability to smoulder. And on that nice example that Dale put up on his slide, that's a hotel in Spain which burned for 2 weeks because the fires kept breaking out and breaking out. So the fire service is going to be an integral part and needs supporting through this. No reason to go into places which aren't safe or haven't been designed to accommodate them. So obviously this is about a very different environment where we've changed. I've mentioned the role of the fire service and why they are so important. But really this indicating very premature failure of ceiling mounted services is covered ground in some respects. We've seen the damage and life loss that can be caused by it, but we are in a different environment and will need a different solution. Messages from the past, well, we have good examples of tragic examples in Harrow Court, Atherson-on-Star, and Shirley Towers, which did result in changing of the electrical wiring regulations to ensure that they stay up on the ceiling in the event of fire to curtail entanglement risks. Now, obviously here we're talking about a slightly different scenario in that these would have been concrete ceilings, but the fixings would have been weak. But hopefully you appreciate from Dale's slides that he's already shown that the scenario here is slightly reversed. Here we have very strong fixings, very, very thick, strong metal fixings going into a substrate that responds differently to fire. So the changes made to the wiring regulations will not actually accommodate this new finding. So I call it really the same but different problem. As I said, weak fixings in a strong substrate. But from Dale's work, we found the loss of strength is remarkably rapid and concerningly rapid in that it is relevant to evacuee and responder timescales. As Dale pointed out, bigger fixings are not always better under fire. And there's a fundamental sort of misunderstanding, is what we're going to show you, of there being a relationship between embedment depth of these large fixings and char formation rates. So often people think of fixing into timber, the char burns back at a certain rate. It might be sort of 0.6 millimeters per minute. But I think what we'll show you here is that is completely irrelevant to a scenario of fixing into timber. Loss of embedment depth is a very tiny part of this when you start to consider conduction of heat into the wood itself and around the threads. Now, this isn't just about the entanglement, crush and electrocution risks that might be posed to evacuees. It does go further than that, in that anything that falls off the ceiling, well, there might be life safety systems in terms of alarm, lighting, smoke management, and even suppression, although we would hope they would self-protect. But also breakdown of passive barriers as large vents dislodge from wall connection points. So even as large vent systems in some of the sort of pictures you see in the top right there fall away, you could be opening up one compartment to another if those were allowed to detach. And as I mentioned, historic changes to wiring regulations really don't afford any protection against this. So we see, I think it's our view when Dale and I discuss this in depth, that really there being an issue in the future, it was a question of when, not if, there was going to be a problem. And it was this is how we presented the Fire Service Research Training Trust, who really agreed. So really for this project, we want to provide focus on the implications for fire service, have good engagement with everyone and the standards making bodies, an output to the cross-reporting systems, because we feel that this is not only a national but international issue that needs addressing with any solutions that we come up, and working with the likes of Nigel to sort out some sort of solutions, and then provide education, which is a key output of the Fire Service Research Training Trust requirements. And already said by Simon nicely, but those that we thanked for their assistance during the testing, and it was very freely and willingly given. But not just in terms of material, but in the expertise also that was provided, we're very grateful for. It really did help the project greatly. So as Dale alluded to, we produced a new rig, which was heavily modified, much more robust. We built it with standards in mind, just in case a deliverable of this would need to be a British standard, which would have a much more rapid turnaround, would be more repeatable, and address some of the comments that we got back, the learning from experience from Dale's tests, one of them being that the fire was maybe a little bit too small when compared to full-scale testing. So that was bulked up as well. And what we found, we got exactly the right sort of char rates as might be expected in full-scale testing going forward. We also wanted to be able to load in different ways. So we were able to load 3 fitting stations simultaneously with different weights, either with winches or actually with suspended weights if space, where space and weight allowed. Well, in looking for a solution, we want to look at all the factors that might contribute to or be resilient against early failure. And the obvious ones are embedment depth, fixing diameter, contact and attachment, mass loading, pilot hole size, and thread pitch, in order to give us some inkling as to where the solutions may lie going forward. Now I'm going to, these are just a few pictures, very similar to Dale's, of what we had. But over on the right-hand side, you'll see we're looking at some very different types of fixings. These are kind of long, skinny things, not the normal sort of hex coach bolts that are specified currently for the suspension of certainly sprinkler systems and many other M&E services. Now, one of the first things that we need to appreciate is how wood responds to fire. And this is absolutely crucial to understanding the solutions to this work. So Dale and I instrumented up one of the CLT panels with thermocouples through it every 10 millimeters, and to see how quickly wood soaked into it and what the loss of char rate is. And this graph actually gives some comfort in that really, once you get above sort of 90 millimeters in depth over a space of a whole hour, really the wood beyond that shows no rise in temperature whatsoever. It's actually crucial that we bear this in mind as to the time period that we're trying to hold services in place for. Clearly it's not infinite, that would be unreasonable, but we need to have a time in mind because this will ultimately determine how much of where the good wood is that's unaffected by temperature. And really the sort of zones that we can think of in terms of damage to wood by fire. Obviously the first one is where we have a loss of material. So there's no structural contribution. We have basically a reduction in embedment depth. We have charred wood, which basically has very little strength to it at all. So again, no contribution of strength there. We then have a zone that is heated, and it does suffer due to the nature of its the lignin lattice and the cellular formation of this biomaterial, which suffers a permanent loss of strength. So it's wood, but it's weaker wood. And then we get to a zone which undergoes temporary heating, which will regain its strength when on cooling. And this is to do with water retention, water being driven out and then reintroduced. And then we have the unheated wood layer, which retains its original strength. So if you keep this sort of imagery in mind, then during this, I'm going to quickly run through these without giving too much detail because there are a lot of tables here. But we looked at embedment depth. Now, if you look at the bottom of all these tables here, these are the ambient retention, the non-fire pull-out weights. And so really around 2 tons here with 100 millimeters. And we found it failing with just a weight of 150 kilograms in just over 1,000 seconds. So I think you can see the speed with which failure is occurring. And as you go less deep, that becomes more rapid, obviously. So embedment depth, we're seeing the impact of embedment depth, but also the acute loss of strength. Similarly, impact of fixing diameter. Now here, this is where we have a skinny bolt M8, but in this case, it's not hardened steel. So in this case, the head melted and it pulled through. So it failed for a different reason to the other two, which remained intact. But as Dale's test showed, the M10 bolt and the M12 bolt. Well, the M12 bolt failed earlier than the M10, the smaller M10 bolt, and this leads us to the idea about conduction along these sorts of fittings having an impact and causing denaturing of the wood around the very threads holding them in place. And then we mentioned mass loading, and really we found it to be quite insensitive to mass loading. Ambient retention, 1.5 tons in this case for an M10 at 100 millimeters. That was tested with the pull-out device. And as we go from 100 to 200, well, these are failing really as much in the same similar sort of time. It's a weak relationship. And even when we go to very low loads, down to just 20 kilograms, we can still see something that should be holding at 2 tons, just weighted by 20 kilograms, failing in a pretty short period of time also. So this isn't really about how much weight you're trying to hold. This is really that when you start heating bolts like this, they really don't want to stay in place, even under their own weight. And I think Dale in his experiments found them to be very loose afterwards, even though they were unweighted. And this was the hypothesis that we came up with, which we think holds true, that early failure is promoted by the efficiency of conduction into the wood itself. And so what these fat fixings are doing, if you think back to that image that I showed of how wood responds in these 4 different layers here, by having a fat bolt that can conduct heat efficiently in, well, you pull down the char layer, you pull down this weakened wood layer, you pull down this temporarily weakened wood layer right into the heart of the wood itself to its embedment depth. And there, that starts to explain the very rapid loss of strength. Does it need to char? We don't know. But even these are wood in weakened states. And wood does lose its strength with temperature very, very quickly indeed. And then our prediction was that if we start to think of using tall, long, skinny fixings like the one in the bottom right, that yes, we can withstand loss of a layer and charring, but because we're conducting less heat in and because they are longer into good wood, that it should perform a lot better. And this is indeed what we did. And whilst we staying with short screws but elongating them out till they become longer and longer, we can start to produce systems which do not fail under any circumstances. And even when we move to so the same sorts of fittings, the same size fittings, but shorter and fatter, I think we get a good comparison there that the solution is in the use of these long, skinny fixings. So really, just to conclude the project, really the key elements for understanding this and putting a solution in place is knowledge of a critical time. How long do you need people to be safe for? Is it 30 minutes, an hour? Is it 2 hours? Because that determines the depth of untouched timber that you get to within CLT. And this is quite a simple thing to characterize, which is very good. So that gives us the interface depth of unheated wood. We need to know the embedment of thread in good wood that will carry on holding retain the loads to their full capability for the full duration. And we need to select fittings that perform as skinny fixings and don't conduct heat into the wood. The final thing, which mustn't be missed, because we did see it, the fittings must be made of hardened steel, because as fittings get skinnier in the normal mild steel type fittings, they would melt and the heads would break off, whereas the hardened steel fittings didn't. Let's bear in mind, it's a salutary moment really to think the findings of this issue was accidental through Dale's work. It was just when we were considering his results and suddenly thought, good grief, this might have some big implications for other systems in a building. It does raise the question about whether new methods of materials are being introduced with sufficient impact analysis and the correct amount of research, and you do start to wonder, what else might be there waiting to be found. But hopefully this work has preempted an issue and will go some way to ensuring that things stay on the ceiling and there's no death or injury resulting from it going forward. So we've really, knowledge sharing is everything now at this point. We've shared it with all these bodies and we're conducting webinars. Dale and I are working up a third paper with the other contributors to really complete the set so that there is a good record of this. I think that's all I have to say, but please do look out for the other ASBP projects which Simon mentioned on damage assessment and repair, through life management of water and moisture in mass timber buildings, and fire sprinklers as an enabler of net zero. That's all I had to say. Thank you very much indeed. I hope that was interesting.
Yeah, fascinating. Thank you very much, both of you. What a great piece of work this is. I'm so pleased to be associated with it. Thank you so much, and incredibly well explained in quite a short amount of time. So I just got a quick point. So you mentioned cross, and I didn't know what cross was, Jim. So can you just explain what cross is and does?
Yes, cross is really gosh, I've forgotten what the acronym stands for. Who's going to tell me?
Yes,
But
I'm afraid I am unable to do that.
It's a construction risk reporting system, or
Collaborative reporting of safer structures, wasn't it?
that's good. Thank you.
you.
So a very reputable website. If you don't subscribe to the newsletters for Cross, you should do, because it highlights all sorts of interesting scenarios. They're all submitted anonymously. Admittedly, I haven't been very anonymous about this, but this isn't like whistleblowing. This is the sharing of research. So I don't think that's a bad thing. But it's a very, very useful site for understanding really what's going on out in the big wide world. And a lot of the failings are to do with how things are implemented and how things are done, but a very, very useful resource for people trying to understand how and why things fail and whether solutions are needed. And it's the ideal vehicle on which to promote this work.
Thank you, Jim, and thanks to Matt for putting the link in the chat. So please have a look at that. All right, so I'm just going to hand over to Nigel. So Nigel hasn't got any slides, but I just wondered, Nigel, if you had any reflections on the work, and thanks once again for getting involved in the project. Yeah, so I'm going to hand over to you and ask you to unmute. Thank you.
Thanks, Simon. Yeah, well, my involvement has been very small. When we see the amount of work that Dale and Jim have done, my involvement is negligible, but nonetheless, been really interested in this work. Congratulate them both on what they've done. So I'm the head of technical at Midfix. We're a long-standing fixing supplier to the construction industry, but in recent years we've evolved in a specialist design engineering business to the mechanical electrical sectors for supports and bracketry for building services and building service plant and equipment. I'll try and keep short, so we're probably running over a little bit on the time, but as the majority would know, following the Building Safety Act and the evolving legislation coming out the back of that, the demand for compliance and, as Ashley said at the beginning, robust evidence around everything we do, especially for anything of safety critical nature, is really critical and being demanded at all levels of the industry. So we spent a lot of time here working on MEP supports, doing a lot of testing on channel-based supports, firstly for ambient conditions, then more latterly for fire conditions over the last 18 months, done a lot of work around fire testing and fire assessing supports. Now, obviously, the majority of supports currently are anchored to concrete because that's the predominant building structure, and we have reliable load data for any anchors fixings into concrete. It's been developed over many years. There's harmonized technical specifications for anchors, been driven by the industry, by the well-funded manufacturers, and we have very reliable load data for fixings into concrete and fire conditions. But to date, we had absolutely nothing for how fixings perform into timber. So the assumption has always been that bigger is better. So this is where this work has been absolutely brilliant in my view. And what's been so nice about it is it's established these principles so conclusively in such a clear-cut way. It's really nice that there's no ambiguity around it. It's the tall thin option wins every time against short and fat. So we've gained a lot. It's put us in a much better position than we were in. So thanks to Dale and Jim, what you've done there. Is it the end of the journey? No, there's a lot further to go.
There were other options, weren't there, Nigel? We looked at maybe putting fixings in at 45 degrees, so their pull-out wasn't in the same direction as gravity, which is an option, but cumbersome. And I think the thin, skinny fixing, I think is probably identified with actually a slight benefit in that there's no need for pilot hole, which reduces the burden. Whilst you may need more of them to support the same weight, it reduces the burden.
Yeah, that's good to mention, Jim, because we looked at it from practical considerations as well. We've got to think of the installers and how they're going to install the fixings. They're working at height, overhead. It's not always easy to get the force you need onto your fixing in that position. So all these things were considered, as you say, trying to fix something at 45 degrees, having to pilot, having to get something deeply embedded on a large diameter and the torque it requires. So this as you say, this conclusion that you've come to, short, tall and thin, is actually assists the installation. So that's good as well. So I mean, ultimately, we'd like to get to a position where we have for fixings into timber in fire conditions what we've currently got for anchors into concrete. So that's just a question of how we move it forward and get to that point. There's two critical considerations for fixings. Supports in fire conditions. That's the premature collapse question, which you've already discussed in the wiring regulation 7671, and then there's a system requirement. So where supports are carrying life safety systems that are required to function for required fire duration, then the support system also has to function for the corresponding fire duration too, and that can, or very often, goes up to 2 hours. So there's currently the testing's looked at up to 60 minutes. Potentially we need to look at going up to 2 hours going forward. So yes, more work to be done, but we've already established, or you have already established, sorry, I should say, conclusively, these basic principles is excellent in my opinion, and steers the way now for any future developments that anyone might want to take up in testing and developing maybe some harmonized technical specification to ensure commonality in the way these things get tested, and that load data is comparable across the industry. So yeah, great work everyone there. As I say, my bit of work's very small, but been pleased to be involved. Thank you.
Brilliant. Thank you, Nigel. So we've got a couple of questions on the Q&A in a minute. If you've got a question, just pop it into there and we'll deal with it as best as we can. The first one is from an anonymous attendee. And a really good question, I thought, and maybe I'll put it to you, Jim. The question is, who is going to be best placed to ensure the safest fixings will be used in mass timber buildings? So for sprinklers and other M&E, is it the sprinkler and M&E equipment manufacturers, or who is it?
Well, I think on the sprinkler one, I'll probably defer to Dale, but as my understanding is that there are specifications for the precise size of fixings used for sprinkler pipe. And I think it's in Dale's gift to change that within the technical bulletins. Is that correct, Dale?
Absolutely, yeah. So basically what we will now do is take the research findings and the conclusions that we have, and we will be developing a specific technical bulletin for the protection of mass timber buildings or exposed timber surfaces. And in that particular technical bulletin, there will be a specification on the types of fixings to be used, the embedment depth and how to use them. So we will take the results from this and it will be put into the sprinkler standards. Now that will just be for the sprinkler standards to the property protection requirements, the LPC sprinkler rules. However, this has also been offered. So the current 12845 sprinkler standard that's used throughout Europe is currently going through a change, and this has been offered to them to incorporate into the British standard or the British adopted European standard. So We will be developing it first. It will then be offered to Europe, and we're probably 2 or 3 years away from that actual information. But the information is there. It's in this report that's been published by ASBP. It will be in a scientific paper, and it is down to the industry to take this forward and produce the best guidance.
Yeah, as we say, this is less of an issue for sprinklers because they will inherently self-protect, and in comparison to other M&E, they're quite light. So the question really is, how does this get into the hands of the M&E providers to ensure that they're much heavier systems which don't have any inherent protection will update accordingly? And I think that's in the hands of BSI to consider following the publication of the Cross report. So I don't have a proper answer, but this is the start of the journey, I think, by telling people.
Yeah, thanks ever so much. And we have been in touch with the Construction Fixings Association, so I invited them to come along to the webinar and to put a news bulletin around. So I'm in touch with Chris Middleton there. If anybody else wants to look at more information, all of the report is as a free download on our website, so it's freely available to anybody and everybody. Please share this news. We want to try and get it out as widely as possible, of course, and that's the sort of key point really of this work. It's no point doing great work if we can't get it out far and wide. Okay, and I've got one further question. We've got 2 minutes. So, hi Charlie, I've got a question from Charlie Law, who has asked for our thoughts on misting sprinkler systems or misting systems. So either Dale or Jim, do you want to come back in on that?
I'll take the lead on that. So yes, mist systems are currently, in the eyes of the insurer, an unregulated market. It's a completely different technology. It's more of a volumetric, gaseous type system that absorbs heat from the fire and displaces oxygen. The study that was conducted was purely to allow a sprinkler system to provide wetting to the surfaces. So misting we considered right at the very beginning. We also considered residential sprinkler systems, but basically when the insurers looked at what they want to make a building more resilient with a sprinkler system, it was a property protection sprinkler system. So mist was sort of cast aside at that particular time, and we focused purely on life safety and property protection sprinkler systems. I don't know if Jim wants to put more to that.
Well, I think NFP have taken quite a view on this as well, that really it's fire sprinkler systems for property protection, that equivalents should not be assumed, but they are obviously a very valuable tool when you are trying to look at sort of life safety and helping egress from the building. The insurer focus is very much on ensuring that the building doesn't burn down at the end of the day and there's something to save and repair.
Yeah, fantastic. So, as we mentioned previously, we do have a report underway looking at sprinklers and how they can act as an enabler for low carbon buildings. So we aim to have that done and out at the end of September. So yeah. All right. Well, thank you so much, everybody. I really appreciate your time and your effort and your energy. Fantastic work, everybody. We're incredibly grateful for everything that you've done, and thank you so much for presenting it so quickly and so clearly. I'm just going to mention the fact that we have another event on next week, which is on a sort of associated subject. So we're looking at reducing plastics in construction. It's a work stream for us, and we have a webinar on next week looking at how we might do this, and also in particular looking at the health implications of plastic and plastic use. Yeah, so do join us for that. So thank you so much, everybody. Thank you so much, audience, for joining us today. I hope you've enjoyed it. Do get in touch if you want to pick up on anything. The report is a free download, as I've mentioned. We will be putting our heads together to think about what should come next. And Nigel, we'd welcome your input on that, as well as anybody else as well. So, all right. So
I think Dale becomes Dr. Kinnersley in the next 2 weeks.
Oh, congratulations.
Tomorrow.
Tomorrow.
Yes.
Fantastic.
Excellent. How are you going to put on a gown and
A bonnet. Yeah. Yeah.
Very well done.
fantastic?
Very
Oh,
well deserved.
well,
Thank
make
you.
sure you send us a photo.
Thank you very much.
Yeah, no, congratulations. Thanks once again. Thanks everybody for joining us today, and look forward to catching up with you and seeing you another time. So thanks one and all. Cheerio, everyone.
Thank
Thanks,
you.
then.
Thank you.